Okay, so let's go back to the strong law of large numbers for Markov chains. So the statement is as follows: if Xn is an irreducible and positive recurrent Markov chain, of course, whenever it's irreducible and positive recurrent, it has a unique stationary distribution. So let that unique stationary distribution be pi. Now you take a function f from S to R, which is either a bounded function or it's non-negative with this pi f, which is the summation fj pi j, which is finite. Okay. So it basically means that if the function f has finite mean with respect to the probability distribution pi j. So then under each pi, so you can just fix any state I, and then under pi, this sample mean will converge to pi f. So this is the sample mean of the fxn's. This will converge to pi f almost surely as n goes to infinity. Now last time for us I had written n equal to 0 to n, but I'll make it n equal to 0 to n minus 1 so that this actually becomes a proportion when we take f to be indicator and so on. So it's not a big change. It's just instead of n, I'm writing n minus 1. Now, last time I stated this theorem, but I didn't give you why one should expect this limit. The reason is as follows. We'll actually show, this will take, I think, 2 more classes to show, not today, is that when Xn is further aperiodic, in addition to being irreducible and positive recurrent, then Xn actually converges in distribution to a random variable X. Of course, an S-valued random variable that has distribution pi. So in other words, what it says is that if the Markov chain is aperiodic, irreducible, and positive recurrent, then under each pi, so if the Markov chain starts with any state I, doesn't matter which state, eventually the Markov chain is going to have the distribution pi. So stationary distribution would be the limiting distribution of the Markov chain. So therefore, heuristically, for large n, expectation of f of xn would be approximately expectation of f of x, because xn converges to xn distribution. So this is just heuristically speaking. And what is the expectation of f of x? X follows distribution pi. Expectation of f of x is just pi f. So therefore, eventually, all of these guys will have expectation pi f. So therefore, you should expect that this mean should converge to pi f almost. So this explains heuristically why one should expect this limit. Then we looked at this specific function which fixes a state k, and then you look at the function which is the indicator that your state I is k. Okay, if you take the function f to be this particular function, then we showed this shows essentially that the proportion, the long run proportion of hitting the state k actually is pi k. Yeah, you have seen this last time. So this tells you that the stationary distribution is the long run proportion of visits to the state k. And this is kind of the natural candidate for stationary distribution as well. So if you have a long run proportion for each state, and that gives you a probability distribution, obviously, if it exists, then it will give you a probability distribution. Then that should be a stationary distribution. I had explained this last time. This is because stationary distribution is a distribution such that if you start with that distribution as your distribution of x naught, then x1 also has the same distribution. So if you start with the long run proportion of various states as your initial distribution, then of course, if you take one more step, the long run proportion is not going to change much, and therefore you will still have the same distribution. So therefore, heuristically speaking, this is a natural candidate for a stationary distribution. And what this says is that if stationary distribution exists and unique when this will happen when the Markov chain is irreducible and positive recurrent. In that situation, the stationary distribution exists uniquely, and it also can be obtained as a limit of the of the proportions of visiting a state K. Okay, okay, so now I'll have a comparison with the periodic case. So we have already shown that in the general irreducible positive recurrent Markov chain, this long run proportion of visiting a state K is essentially pi K. And then here is an exercise for you. It's just direct application of bounded convergence theorem. If we just apply bounded convergence theorem, then this converges to this, and then the expectation will converge to the expectation. But this side is non-random, so therefore no change will happen. But this side, expectation of a sum will just become sum of the expectation, which are all the probabilities, which will give you this. So therefore, you will get that this Cesaro limit of this PIKNs will be pi k. This is the Cesaro limit of the PIKNs, right? This is the mean of the PIKs where n runs from 0 to n minus 1. PIKNs when n runs from 0 to n minus 1. So therefore, this Cesaro limit is actually pi k. Now this holds even when the chain is periodic. In the aperiodic case, we can actually prove something stronger. We can show, as I said, we'll be able to show that Xn converges in distribution to pi under each Pi, which means that for each state K and each state I, if you start the Markov chain from I, then the Pi, okay, of Xn equal to K converges to pi K. So this is exactly what this statement means. And then of course, that just means that PIKN converges to pi K as n goes to infinity. Now, of course, if this convergence holds, then Cesaro convergence will also hold. So this is the strongest statement. So in the aperiodic case, you can actually prove that PIKN itself converges to pi K. In the periodic case, we won't be able to show this. However, the periodicity will be killed when you take this Cesaro sum. Okay, so, and you will have the convergence. So therefore, in the periodic case, we have the actual convergence. In the aperiodic case, we have the convergence of the Cesaro sums, which is slightly weaker. Okay, so this is the statement of SLLN for Markov chains, and what we will do is that we are going to prove when f is non-negative and pi f is finite. The case when f is bounded will be left as an exercise. So let's start with a computation. Let's try to write the limit slightly differently when f is non-negative. So fix an I in S. So note that this I has to be positive recurrent because the chain is assumed to be positive recurrent. So each state is positive recurrent. So if you fix a state, that's going to be positive recurrent as well. And the definition of pi f is just this sum. Now note that pi j, obviously since I is positive recurrent, pi j can always be written as this. So here, whatever I have written here, this thing is pi j. Okay. This is the expected number of visits to j in the first excursion to I, okay, starting from I, of course. Okay. And you divide it by the expected length of the excursion. So if this whole quantity is just pi j, we have already shown that. So therefore, I've just written the form of the pi j. Now this is just, this can come out. You can just, I've just written the things slightly neatly. That's why I haven't done anything here so far. I've just divided, I've brought this out of the summation. That's the only thing I've done. This has no j in it. I've just brought it out of the summation. Now expectation of a sum is going to be sum of expectations because everything is non-negative here. F is assumed to be non-negative. All the indicators are non-negative, so everything is non-negative. So therefore, by the application of monotone convergence theorem, you can see that this can go inside the expectation. So what you will get, therefore, this will be expectation of this whole sum. Okay, and also expectation is linear, so this fj's also can go inside the sum and so on. Now again, everything is non-negative, so we can interchange the sum. That's because of Fubini. Okay, so interchange the sum inside the expectation, of course. But then you observe that this sum here, this is the sum of fj indicator xn equal to j. This is just f of xn. Why? That's because what is f of xn? F of xn takes the value fg when xn takes the value g. Right? So therefore, f of xn is just this sum. This rate quantity here is equal to this quantity. So therefore, what this tells you is that pi of f can be written as this form, in this form. So therefore, what we have been able to achieve is that we have expressed the limit in a different form, which actually will be useful in the proof.